Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. Today we are going to discuss about the module Basics of Communications Transmission Lines from the paper Electronics. So students, let us see what we are going to learn in this module. First, we will study the basics of electronic communications. Second, we will study the base of communication, that is electromagnetic waves and their energy. Thirdly, we will study about the transmission lines and their different types. Lastly, we will study about the parameters and equations of transmission lines. So let us start with a basic introduction about the module. Today, communication enters our daily lives in so many different ways that it is very easy to overlook the multimode of its facets. The telephones at our hands, the radios and the televisions in our living rooms, the computer terminals in our offices and homes, and our newspapers are all capable of providing rapid communication from every corner of the globe. So, in the most fundamental sense, communication involves implicitly the transmission of information from one point to another through succession of processes. The electronic communication deals with the electronic devices, circuits, communication equipments like transmitter, receiver, and integrated circuits ICs. It also deals with basic electronics, analog and digital transmission, and reception of data. Electronic communication also plays a crucial role in satellite communication, microwave engineering, antenna, and wave propagation. Electronics communication. Following is a simplified block diagram of an electronic communication system that includes a transmitter, a transmission medium, a receiver, and a system noise. A transmitter is a collection of one or more electronic devices or circuits that converts the original source information to a form which is more suitable for transmission over a particular transmission medium. The transmission medium or communication channel provides a means of transporting signals between a transmitter and a receiver, which can be simple as a pair of copper wires or as complex as sophisticated microwave, satellite, or optical fiber communication systems. Now, the last one is a receiver, which is a collection of electronic devices and circuits that accepts the transmitted signals from the transmission medium and then converts those signals back to their original form. So students, there are two basic types of electronic communication systems. First one is the analog communication system, in which energy is transmitted and received in the analog form. Second one is the digital communication, which covers a broad range of communication techniques, including digital transmission, and digital radio. Comparison between the analog and digital communication. Analog signals are the signals having continuous values, so they are used in many systems. Although the use of analog signals has been declined with the advent of cheap digital signals. Analog systems are very tolerant to noises, makes good use of bandwidth, and are easy to manipulate mathematically. Analog signals requires hardware receivers and transmitters that are designed to perfectly fit the particular transmission. For example, one is working on a new system and he or she decides to change the analog signal, then one need to completely change the transmitters and the receivers. Whereas in the digital signals, which are the signals that are represented by binary numbers, that is 0 and 1. The 1 and the 0 values can correspond to different discrete voltage values, and any signal that does not fit into the scheme gets round off. The digital signals are intolerant to noise and they can be completely corrupted in the presence of excess noise. In digital signals, noise can disrupt the original signal and it can change the signal, resulting in the false data. So, although the analog systems are less expensive in many cases than the digital ones, for the same application, digital systems offers much more higher efficiency, better performance, and much greater flexibility. Transmission lines. The transmission of information as an electromagnetic signal that occurs as a transverse electromagnetic wave. With metallic conductors in transmission lines, they confines the TEM wave to the vicinity of the dielectric surrounding the conductors. As a result, some aspects of the transmissions are best treated in terms of the distributed circuit parameter of the line, while others requires the wave properties of the line to be taken into account. Now let us discuss about the electromagnetic waves and energy. All electronic communication systems send information from one point to the other by transmitting electromagnetic energy from the sender to the intended receiver. This electromagnetic energy can travel in various modes as a voltage or current through wires, as radio emissions through air or the vacuum of space, or as light. Wavelength of light wave is an important parameter which can be measured as the distance between the negative peaks, 0 points, or any point on the waveform, as long as the same point is used on each adjacent cycle for measurement. So, wavelength is given by velocity divided by the frequency. The speed at which a wave travels depends on the substance or the medium through which it is traveling, and it is called as the propagation velocity. Wavelength is important because many aspects of the system design and types of electronic components that must be used are determined by the wavelength in the systems. The next important parameter is a transmission frequency. The total electromagnetic frequency spectrum showing the approximate locations of various services. The useful electromagnetic frequency spectrum extends from approximately 10 kHz to several billions of hertz. The lowest frequencies are used only for communications in water. Next one is the bandwidth. Bandwidth of an information signal is simply the difference between the highest and the lowest frequencies contained in the information, and the bandwidth of a communication channel is the difference between the highest and the lowest frequencies that the channel will allow to pass through it. Last one is the information capacity, which is nothing but a measure of how much information can be propagated through a communication system, and it is a function of bandwidth and transmission time. Transmission lines. Wave propagation in unbounded media is the media of infinite extent. So, unguided wave propagation means there is a uniform plane wave exists throughout all the space, and electromagnetic energy associated with the wave spreads over a wide area. It is used in radio or TV broadcasting, where information being transmitted is meant for everyone who may be interested. However, this type of wave propagation will not work for telephone conversation, where the information is received privately by one person. Thus, information needs to be transferred by guided structure from the source, maybe transmitter, to the load like antenna. So, some of the examples are transmission lines and waveguides. Interchange of electric and magnetic energy give rise to the propagation of electromagnetic waves in space. More specifically, time-varying magnetic field induces electric field, that is Faraday's law, and time-varying electric field induces magnetic field, generalized Ampere's law. This interrelationship also occurs along conducting or dielectric boundaries and can give rise to a wave that are guided by such boundaries. These waves are important in guiding the electromagnetic energy from the source to the load. So examples are dielectric guides, hollow pipe waveguides, two-conductor transmission lines. Let us now discuss the types of transmission lines. Transmission line, when broadly consists of two or more parallel conductors which are used to connect a source to the load. Examples are coaxial cable, a two-wire line, a parallel plate or a planar line, and a microstrip line. In a transmission line, the metallic conductors confine the TEM wave to the vicinity of the dielectric surrounding the conductor, due to which some aspect of the transmission are best treated in terms of distributed circuit parameters of the line. Basic types of transmission lines are two-wire line and coaxial line. Transmission line with respect to ground may be categorized as balanced, that is two-wire line, and unbalanced or coaxial line. In coaxial line, the outer conductor forms a shield which confines the wave to the space between the conductor so that the radiation from the line is negligible. However, the line is basically unbalanced since the external capacitance is between the outer conductor only and the ground. Primary line constants. A transmission will have series resistance and inductance, which together go to make up the series impedance of the conducting wires, and shunt conductance and capacitance of the dielectric between the conductors, which go to make the shunt admittance of the line, as shown in this figure. So the primary line constants like R, L, G and C are the constants and do not vary with the voltage and the current. The series resistance R increases with frequency as a result of the skin effect. The inductance L is almost independence of frequency for open lines, but tends to decrease with increasing frequency for screened cables. So the two-wire line is usually operated in the balance mode, the conductors being arranged so that they present equal capacitances to the ground. Radiation can occur from a two-wire line since the TEM wave can radiate out from the line as well as along it, as it is shown in this figure. And the two-wire line is less expensive than the coaxial line and is used for the majority of low frequency signals. In general, in any transverse plane, E lines passes from one conductor to the other, giving a voltage between the conductors for that plane. So B lines surrounds the conductors corresponding to the current flow in a conductor and an equal but opposite current flow in the other. So both V and I, also E and B, are the function of distance along the line. So the L, the capital L, is associated with the flux produced by the oppositely directed currents in a pair of parallel conductors. So when L or when I varies with time, there is a voltage change along the line, that is V is equal to L di by dt. Similarly, distributed C produces displacement current between the conductors when the voltage is time varying and leads to change in the current flowing along the conductors. That is I is equal to C dV by dt. So the interrelationship leads to the wave equation for V and I along an ideal lossless transmission line, R equal to 0 and G equal to 0. So let us now discuss about the transmission line parameters. Transmission line problems are usually solved using EM field theory and electric circuit theory. So we'll use the circuit theory over here, and the transmission line parameters, as we have already discussed, are R, L, G and C, which are not discrete or lumped, but they are distributed. Parameters are uniformly distributed along the entire length of the line, which is clearly shown in this figure. For each line, the conductors are characterized by sigma C, mu C, epsilon C equal to epsilon naught, and homogeneous dielectric separating the two conductors by sigma, mu and epsilon. Now here R is the AC resistance per unit length of the conductors, which is inversely proportional to sigma C. G is the conductance per unit length due to the dielectric medium, directly proportional to sigma. C is the capacitance per unit length due to dielectric. L is the external inductance per unit length of the conductor. So the effect of internal inductance L in is negligible at high frequencies at which most communication systems operate. So for each line, LC equal to mu epsilon and G by C equal to sigma by epsilon. Let us consider the coaxial line connecting the generator AC source to the load. When switch S is closed, inner conductor is positive with respect to the outer shield so that electric field is radiated outward. Magnetic field H encircles the current carrying conductor. So now the pointing vector, that is E cross H, points along the transmission line closing S, which creates the disturbance resulting in a TEM wave as shown in this figure. Let us now derive or discuss the transmission line equations. Transmission line supports a TEM wave, which means that electric field E and magnetic field H on the line are transverse to the direction of wave propagation. The important property of TEM waves is that E and H are uniquely related to V and I respectively. That is, V is equal to minus integral E vector dot dl vector, and I is the closed integral over H vector dot dl vector. This wave is non-uniform plane wave by means of which its power is transmitted through the line. Therefore, we can use V and I in solving the transmission line problem instead of solving the field equations E and H, that is solving Maxwell's equations and boundary conditions. Now consider an incremental portion of length delta Z of a two-conductor transmission line. So the equivalent circuit of absorption of the line, which is shown earlier, the model is called as the L-type equivalent circuit. Now here we assume the wave propagation along the positive Z direction, and this is from the generator to the load. So by applying the Kirchhoff's voltage loop to the outer loop circuit, we have VZT equal to R delta Z IZT plus L delta Z delta I by delta T plus VZ plus delta ZT. So minus VZ plus delta ZT minus VZT divided by delta Z is equal to RIZT plus L delta IZT by delta T. So now taking the limit delta Z tends to 0, it leads to minus delta V by delta Z equal to Ri plus L delta I by delta T. Similarly, if we apply the Kirchhoff's current loop to maintain the node of the circuit, it gives IZT equal to IZ plus delta ZT plus delta I. IZT is equal to IZ plus delta ZT plus G delta Z V Z plus delta ZT plus C delta Z del V Z plus delta ZT by del T. That is minus IZ plus delta ZT minus IZT divided by delta Z equal to GV Z plus delta ZT plus C del V Z plus delta ZT by del T. That is, if delta Z tends to 0, we have minus delta I by del Z equal to GV plus C del V by del T. If we assume the harmonic time dependence so that Vzt equal to Vsz exponential j omega t, Izt equal to Isz exponential j omega t, where Vsz and Isz are the phasor forms of Vzt and Izt respectively. So now putting these values in the equation 1, we get minus del Vsz exponential j omega t by del z equal to r Isz exponential j omega t plus L del Isz exponential j omega t by del t, or we can say minus del Vsz by del z equal to r plus j omega L multiplied by Isz. Similarly, putting equation 3 and 4 in equation 2, we get minus del Isz by del z equal to g plus j omega c Vsz. Here Is and Vs are coupled. So in order to separate them, we take the second derivative of Vs in equation 5 and 6 and we get d square Vs by dz square equal to r plus j omega L multiplied by g plus j omega c Vs, or d square Vs by dz square minus gamma square Vs equal to 0, where gamma is alpha plus j beta equal to root of r plus j omega L multiplied by g plus j omega c. Similarly, taking the second derivative of Is in equation 6 and using equation 5, we get d square Is by dz square minus gamma square Is equal to 0. So the equation 7 and equation 9 are respectively the wave equations for V and I, similar in the form obtained for the plane waves. Here gamma is the propagation constant meter inverse, alpha is the attenuation constant in Nepers per meter or decibels square per meter, and beta is the phase constant in radians per meter. So the wavelength is given by lambda is 2 pi by beta and wave velocity, that is u, is omega by beta equal to f lambda. The solution of linear homogeneous differential equations 7 and 9. They are expressible as a sum of forward and backward moving waves, that is Vz equal to V0 plus exponential minus gamma z plus V0 minus e to the power plus gamma z, Iz equal to I0 plus e to the power minus gamma z plus I0 minus e to the power plus gamma z, where V0 plus, V0 minus, I0 plus, I0 minus are the wave amplitudes. Here plus and minus respectively denotes the wave traveling along the positive z direction and the negative z direction. So therefore, instantaneous expression for Vzt is equal to real Vsz exponential j omega t, which is given by Vzt equal to real of Vsz exponential j omega t, which is equal to, after putting this value of Vsz, we get real of V0 plus exponential alpha plus j beta multiplied by z plus V0 minus exponential alpha plus j beta multiplied by z, this whole multiplied by exponential j omega t. So this is equal to, after separating the terms, equal to V0 plus exponential minus alpha z cos omega t minus beta z plus V0 minus exponential plus alpha z cos omega t plus beta z. So Vzt will be equal to V0 plus exponential minus alpha z cos omega t minus beta z plus V naught plus exponential plus alpha z cos omega t plus beta z. So students, let us summarize what we have learnt in this module. First, the electronic communication deals with the electronic devices, circuits, communication equipments like transmitters, receivers, and ICs. It also deals with the basic electronics, analog and digital transmission and reception of data. Secondly, we also learned about the transmitters and the transmission medium, a receiver, and a system noise. So, there are two types of electronic communication, namely analog and digital communication, which were discussed in detail in this module. Next, we also discussed about that all electronic communication systems, they send information from one point to the other by transmitting the electromagnetic energy from the sender to the receiver. This electromagnetic energy can travel in various modes as a voltage or current through wires, as radio transmission through air or the vacuum of space, or as light. Next, we discussed about the transmission lines, that is their parameters, which were calculated using EM field theory and electric circuit theory. In this, coaxial line has been considered, which connects the generator as a source to the load. The transmission line equations have also been studied, where the solution of linear homogeneous differential equation has been calculated in terms of the voltage and the current amplitudes. Lastly, we also derive the expression for the instantaneous value of the voltage. Thank you.